Hydrates are an extension of ionic compounds, and just like the word hydrate implies, it means that there's water that is incorporated into the ionic compound's formula. So there's a specific number of waters for each formula unit, or another way to say that is for each empirical formula number of elements, there's a specific number of water molecules. Now this is a reversible process, so the water that is in the hydrate can be heated up and driven off by using an oven or some other method of adding heat. So we can remove the water by heating it up. Okay? Some of these compounds will absorb water from being open to the atmosphere. When we write the formula, the way that we show the waters is by putting a dot. So we add a dot between the ionic compound formula and the number of waters that are included to show that they are indeed incorporated into that formula. To name them, it is a pretty simple process. So we name the ionic compound, and then we add a prefix telling us the number of waters with the word hydrate following it. So for example, CoCl2, Co is a transition metal, so we do need to include the Roman numerals in parentheses. So it's cobalt 2 chloride, because there's 2 chlorines. And then because there's 6 waters, we're going to use the prefix hexy. And so these prefixes are based on the prefixes that we see for most geometric shapes. So like a triangle, a pentagram, right? So these are pretty common prefixes representing a specific number. Some that you may not be as familiar with are hemi for half, and the reason we can have half is because the ionic compound is sharing a water between 2 formula units. We have mono for 1 and di for 2. So for example, CaSO4 with half a water is going to be calcium sulfate, no Roman numeral required because calcium is in column 2. And then hemi, so hemi represents that 1/2 hydrate. Calcium sulfate, hemihydrate. Now, ionic compounds that are hydrated do have different chemical properties, and they can look very different from the ionic compound without water. And without water is what we call anhydrous, without that hydrate. Okay, so for example, our copper chloride, when it's hydrated, is much more of a red color, but when it is in its anhydrous form, it's more of a blue-purple color. And so these can be used to detect when water is present, or even to absorb water if we're trying to remove it from a particular atmosphere or area. Pause the video to see if you can come up with the formula or the name for these 2 examples. Magnesium sulfate heptahydrate. So we do not have Roman numerals included. Magnesium is in column 2 of the periodic table, which means it is a +2 charge. Sulfate ends ATE, which means that it's sulfur with another element. Most commonly, that other element is oxygen when we see that ATE ending. For sulfate, it is always SO4 with a -2 charge. Hepta, if we look at our table, hepta stands for 7, and then hydrate is H2O. So to make our ionic compound, we need to balance the charge. We have a +2 and a -2. We just need one of each in order to make a total charge of 0. We put the dot, and then 7H2O. when we name NiCl2.6H2O, Ni is nickel. Nickel is number 28 on the periodic table, which is a transition metal, so we do need to include the charge. So because we have 2 chlorines and each chlorine is a -1 charge, that means that in order for the whole thing to be 0, the nickel has to be a +2. And so we need to include that +2 Roman numeral in parentheses. And then Cl2, it's only a single element, so that is chloride. And then .6H2O, so 6 is hexahydrate.